बिस्मिल्लाहिर्रहमानिर्रहीम। डियर स्टूडेंट्स, अस्सलाम वालेकुम। आज के लेक्चर में हमने फिज़िक्स सेकेंड ईयर के कोर्स से डिस्कस करना है कूलम्ब लॉ, इलेक्ट्रिक फील्ड और इलेक्ट्रिक फील्ड इंटेंसिटी, रिप्रेजेंटेशन ऑफ इलेक्ट्रिक फील्ड लाइंस, इलेक्ट्रिक फ्लक्स, गाज़ लॉ और गाज़ लॉ की एप्लीकेशंस। तो स्टार्ट लेते हैं कूलम्ब लॉ से। आपसे दरख्वास्त होगी कि अपने क्लास नोट्स या बुक या किसी तरह के नोट्स अपने सामने रख लें। तो कूलम्ब लॉ यूज़ होता है टू फाइंड द मैग्नीट्यूड ऑफ अ कूलम्ब फोर्स बिटवीन 2 पॉइंट चार्जेस। कूलम्ब फोर्स जिसे हम इलेक्ट्रोस्टैटिक फोर्स भी कहते हैं। According to this law, force of attraction or repulsion between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. अगर बात की जाए इसकी एक्सप्लेनेशन की, तो सबसे पहले हमने कंसिडर करने हैं 2 पॉइंट चार्जेस Q1 and Q2. Say distance between them is R. According to this law, F is directly proportional to the product of the charges. Second equation is F is inversely proportional to the square of the distance between them. Combining these two equations, F is proportional to Q1 Q2 divided by R square, where K is constant and its value depends upon the system of units and the medium between the charges. If the system of unit is SI system and the medium between the charges is air or vacuum, then value of K is 1 by 4 pi epsilon naught, equal to 9 into 10 raised to power 9 Newton meter square per Coulomb square, where epsilon naught is the permittivity of free space and it is equal to 8.85 into 10 to the minus 12 Coulomb square per Newton meter square. Under this condition, Coulomb law become F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square. Now if the medium between the charges is other than air or vacuum, then K is equal to 1 by 4 pi epsilon naught epsilon R, where epsilon R is relative permittivity, means permittivity of a medium as compared to air or vacuum. Under this condition, say the Coulomb force is F prime, and F prime is equal to 1 by 4 pi epsilon naught epsilon R Q1 Q2 divided by R square. Here 1 by 4 pi epsilon naught Q1 Q2 divided by R square is F. So we can say that F prime is equal to F divided by epsilon R, or epsilon R is F divided by F prime. That is, the relative permittivity of a medium is the ratio of Coulomb force between the two charges, between 2 point charges, when there is no medium between the charges, and the Coulomb force when there is a medium between the charges is other than air or vacuum. And the last section we are going to represent the Coulomb law in vector form. In vector form, say R12 is a unit vector in the direction of F12, where F12 is a Coulomb force directed from charge 1 to charge 2, and R12 is the R21 is the unit vector in the direction of F21, where F21 is the Coulomb force directed from charge Q2 to Q1. So in vector form, F12 is equal to K Q1 Q2 divided by R square into R12 equal to minus K Q1 Q2 divided by R square into R21, because R12 is equal to minus R21. So here F12 is equal to minus F21. Hence we can say that Coulomb forces are the action and reaction forces. Next is the electric field. And what about the electric field? It is the space around a charge within which it can exert Coulomb force or electrostatic force on other charges. And the strength of the electric field is called electric field intensity. Electric field intensity is the electric field intensity at a point is the Coulomb force acting per unit positive charge on a point which is placed to that point. That is it is the electric field intensity at a point inside the electric field is the Coulomb force acting per unit positive charge placed at that point. That is F is equal to, E is equal to F by Q. It is a vector, its unit is Newton per Coulomb. It is directed away from the charge if charge is positive, and it is directed towards the charge if charge is negative. So electric field intensity is a single vector quantity which can be used to determine the direction and the magnitude of electric field intensity. Next is the electric field intensity due to a point charge. In order to calculate electric field intensity at a point inside the electric field, say P, let we place a test charge, say Q0, at a distance R from the source charge Q. So electric field intensity at point Q is F divided by Q0, but F is K Q1 Q2 divided by R square. That is K, Q1 is Q, Q2 is Q0 divided by R square divided by Q0, and result is KQ divided by R square, or 1 over 4 pi epsilon naught Q divided by R square. So the electric field intensity due to a point charge is 1 by 4 pi epsilon naught Q divided by R square. This equation shows that electric field intensity depends upon the source charge, not on the test charge. Next is the electric field line or electric field lines. What about the electric field line? These are the imaginary lines which are drawn inside the electric field used to represent the an electric field. Defined as the path on which a positive free isolated charge move inside an electric field. What about these field lines, if the lines are due to positive charge, then the line always directed away from the charge. If these lines are due to a negative charge, then they are directed away from the they are directed toward the charge. If the lines are due to a set of positive and negative charge, then lines are directed from positive to the negative charge, mean they start from positive charge, terminate at the negative charge. In case of two positive charges, these lines repel each other because the same charges repel each other. Secondly, no two lines can cross each other. So there are some points where there is no electric field or field line is present. Those points are called neutral points. In case of two plates, a positive and negative plates placed parallel to each other, field lines are always directed from positive to the negative plate. In case of a single positively charged plate of infinite size, these lines are always directed away from the plate, and in case of a single plate of negative charges of infinite size, field lines are directed toward the plate. So what about the electric field line? Electric field lines are the lines used to represent the direction of electric field, and direction of electric field is always tangent to a line, and these lines always start from a positive charge, terminate at the negative charge. In case of single positive charge, they are directed radially outward from the charge. In case of a negative charge, directed inward to the charge. And one thing which is very important about these lines, no two lines cross each other. Next is electric flux. Electric flux is basically electric flux is the number of field lines passing through an area inside an electric field. So this is an area, these are the field lines, the line passing through an area is the electric flux. In case of an area which is plane and electric field is uniform, then electric flux is the scalar product of E and A. Where E is the electric field intensity and A is the area vector or the normal vector. Normal vector or the area vector is a vector which is always drawn perpendicular to the surface. It is drawn perpendicular to the surface. Secondly, its magnitude is equal to the surface area. In case where the area is not plane, it is curved, then in order to calculate the electric flux, we have to divide the whole surface in number of small areas, each having area vector, say 1, A2, A3 up to so on AN, and finally the total electric flux is the sum of electric fluxes through each area, that is phi is equal to phi 1 plus phi 2 plus phi 3 plus so on plus phi n. What about the electric flux? It may be zero, may be positive, it may be negative. If phi is 0, if theta is 0, cos 0 is 1, electric flux is maximum and equal to En. If phi is 90, that is theta is 90, mean, say this is your area vector, this is your area vector, for this area, or the normal vector is like this, say field lines are like this, then like this, then under this condition theta is 90 degree, theta is the angle between the area vector and the direction of field lines, so electric flux will be 0. If this theta is 180 degree, or theta is such a theta that for which cos theta is negative, electric flux will be negative. Finally, Gauss's law, important law used to find out the value of electric field intensity inside the electric field. One of the fundamental law, that is the Gauss's law. According to this law, total electric flux through a closed surface is always equal to Q divided by epsilon naught, where Q is the total charge enclosed by the closed surface. Then you have to prove this law. In order to prove this law, let me consider a closed surface, say a closed surface in a spherical shape where a charge Q is placed at the center of the sphere, where in order to calculate the total electric flux through the sphere, we have to divide the whole surface in number of small patches, each having area A1, A2, A3 up to so on, up to AN. As we know that every point on the surface of the sphere is equidistant from the center of the sphere, so the magnitude of E will remain same everywhere on the surface of the sphere. So the total electric flux through the sphere will be phi equal to phi 1 plus phi 2 plus so on plus phi n. E A1 cos 0, E A2 cos 0 plus so on plus E AN cos 0. Cos 0 is 1, so E A1 plus E A2 plus so on plus E AN. E is common, A1 plus A2 plus so on plus AN. E is Q divided by R square, and A1 plus A2 plus so on is the total area of the sphere, that is 4 pi R square. But K is 1 by 4 pi epsilon naught Q divided by R square into 4 pi R square. Cancellation give us Q divided by epsilon naught, which is the mathematical proof of Gauss's law. Now, if the surface is not in regular shape, then let me consider the charges Q1, Q2, Q3 up to so on, up to Qn are enclosed by the surface. Then the total, in order to calculate the total electric flux, we have to draw number of small spheres around each charge, and the total electric flux through the surface will be the sum of the all electric fluxes through each sphere, that is phi is equal to phi 1 plus phi 2 plus phi 3 plus so on plus phi n, that is Q1 divided by epsilon naught plus Q2 divided by epsilon naught plus so on plus Qn divided by epsilon naught. 1 over epsilon naught is common, Q1 plus Q2 plus so on plus Qn, that is Q divided by epsilon naught, where Q is the total charge enclosed by the closed surface. This is what about the Gauss's law. Let me start with some applications. Some applications of Gauss's law, that is the location of excess charge on a conductor. First, second one, the electric field intensity due to infinite sheet of charge, and third one, the electric field intensity between two oppositely charged plates. First, the location of excess charge on a conductor. One thing which you must remember, for our first application, that whenever an extra charge means a charge is given to a conductor, it will always reside at the surface of the conductor. It will always reside at the surface of the conductor. It will stay at the surface of the conductor. Let me prove this statement. The statement is where an excess charge will reside. It will reside at the surface of the conductor. Let a charge is given to the conductor. Say the positive charge is given to the conductor. In electrostatic equilibrium, E is 0 inside the conductor. At the E is 0 inside the conductor, so according to the Kazakh law, phi is equal to Q divided by epsilon naught. E into A is equal to Q divided by epsilon naught. As E is 0, E is 0, so 0 is equal to Q divided by epsilon naught, which implies that Q is equal to 0. That is, no charge is imposed by any Gaussian surface inside the conductor. Second one is the electric field intensity due to an infinite sheet of charge. For this purpose, let we consider a sheet of charge of infinite size on which positive charges are uniformly distributed. As we know that in case of positive charges, field lines are always directed away from the plate. So the field lines are always directed away from the plate, let the surface charge density of this plate is sigma, and sigma is the total charge per unit area. Charge per unit area, that is sigma. So the total charge on the plate will be sigma into A. In order to apply Gaussian law, let we consider a closed surface, a Gaussian surface in form of a cylinder. In case of cylinder, it has three surfaces, two planes, this one two, and one is curved. So for these two surfaces, this and this surfaces, E and A are parallel. And what about this surface? E and A are perpendicular. So the total electric flux is phi 1 plus phi 2 plus phi 3. When E and A are perpendicular, then electric flux is 0, because EA cos 90 is equal to 0, because cos 90 is 0. So the electric flux is phi 1 plus phi 2. Phi 1 is EA and phi 2 is again EA, because EA cos 0 and EA cos 0 is 1, so EA cos 0. So phi A is equal to 2EA. But what about phi? Is the Q divided by epsilon naught according to the Gaussian law, 2EA. But Q is sigma into A. Sigma into A divided by epsilon naught is equal to 2EA. Cancellation gives us E is equal to sigma divided by 2 epsilon naught, and in vector form E is equal to sigma divided by 2 epsilon naught into R unit vector. R unit vector directed away from the plate in case of positive charges, and in case of negative charges it will directed toward the plate. The result will remain the same in case of negative plate, but under this condition E is equal to sigma divided by 2 epsilon naught into minus R unit vector, that is minus sigma divided by 2 epsilon naught into R unit vector. Finally, the last topic of the day is the electric field intensity due to two oppositely charged plates. So here let me consider two oppositely charged plates of infinite size placed parallel to each other. Let we calculate electric field intensity due to these two oppositely charged plates. Again, let we consider a closed surface. Say a closed surface in form of a square. A closed surface in form of a square, where the one face of the surface is enclosed within the positive plate. So in this case, there are three surfaces for which we are going to calculate the electric flux. These two surfaces, if say this is our square shaped book. For this surface, say electric field lines are directed like this. For this surface, E and A are perpendicular. Here again it is perpendicular. So for these two surfaces, electric flux will be 0. And what about this surface? For this surface, it will be E into A, because E and A are parallel. So E and A parallel. So the electric flux, total electric flux, is now in simply E into A. And it is E into A, but sigma is equal to, the electric flux is equal to Q divided by epsilon naught, according to the Kazakh Law. And Q is equal to sigma into A. Sigma into epsilon is E into A. Cancellation gives us E is equal to sigma divided by epsilon naught. For a single plate, it was sigma divided by 2 epsilon naught. But here it is sigma divided by epsilon naught. That is, if we multiply and divide by 2 sigma divided by 2 epsilon naught. That is now electric field intensity twice the electric field intensity due to a positively charged or a negatively charged plate, mean due to a single plate. So remember, whenever a charge is placed between the plates, so so in case of oppositely charged plates, the electric field intensity between the plates is twice the electric field intensity due to a single sheet of charge. And if we place the charge outside the plates, in case of where a point is outside the plates, then one of the plate attract the charge, say this is the positive charge, and other will repel the charge, net field intensity will become 0. So in case of two oppositely charged plates, electric field intensity between the plates is twice the electric field intensity due to a single sheet of charges. And outside the plates, it will be 0. And if two plates of similar charges are placed parallel to each other, then electric field intensity between the plates will be 0. And outside the plates, it will be twice the electric field intensity due to a single sheet of charge. And we know that electric field intensity due to a single sheet of charge is sigma divided by 2 epsilon naught, and due to two oppositely charged plates, it will be sigma divided by epsilon naught between the plates, and outside the plate it will be 0. In case of two plates of same charges, it will be 0 between the plates, and outside the plates it will be sigma divided by epsilon naught. That's end.